So I'm first going to talk a little bit about data at Slack and how it applies to machine learning. And then I'm going to talk about how we built a privacy-preserving model for search ranking. So what is Slack? By a show of hand, who has never heard of Slack before? All right, cool. So I won't have to explain too much about how it works. So at its core, Slack is a communication platform. So it's a way for people to share messages with each other or files or really anything from third-party integration. Most of the conversations are centered around channels. So channels usually are about a particular topic or a particular project. And so data at Slack has kind of two interesting characteristics from a machine learning perspective. On the first, and within an organization, and here I'm using organization in the Slack sense, so I might use workplace, team, but basically your Slack team. So within your within an organization, data is mostly public by default, but at the same time, across organizations, data is strictly private by default. So what do I mean by public by default? Well, if you look at traditional messaging or traditional communication platform, like email, for example, when you want to send a message, one of the first things you do is you pick a list of recipients. From there on, you and the recipients are the only people who have access to that data. So if there's someone else on the company that might find that data useful and they're not listed as a recipient, they're just never going to have access to that data. On the other end, in Slack, data is mostly sent through public channels. So instead of picking a list of recipients, you pick a channel. That channel usually, most conversation happens in public channel. That channel is available to anyone at the company, and so anyone at the company has access to that data. This also applies to new users. So if someone joins the team later, that person has access to everything that was ever said in any public channel within the organization. So what does that mean for machine learning? Well, this is actually a great source of data for building machine learning models. So there's all this public data available within every organization. At the same time, it makes machine learning a very valuable tool to help users sift through that data. And that's what most of the search and discovery team does here in New York, is to try to figure out how to build machine learning models to help users find the information that's most relevant to them. The second characteristic is that, as I said, across organization, data is strictly private by default. So what does that mean? Well, if we have two organizations, organization A and B, if someone in organization A posts a message in the cats channel, we really don't want it to end up in the burgers channel on organization B, right? So our customers trust us with their data, and we have to do everything we can to make sure data doesn't leak between teams. So here's an example of something we don't want to happen. Let's say we're training a topic model, and we're using data from multiple teams, and one team is going through some hard times, and they're talking a lot about layoffs. If our topic model learns to associate layoffs with the name of that company, and we're to reuse that model across different teams, someone querying that model from a different team could infer that association, and that would be bad for our customers and bad for us. So again, what does that mean for machine learning? Well, the models we build really have to respect these strict privacy boundaries between organizations, right? They have to do it both explicitly, so we don't have to, we shouldn't surface data from one team and another team, and we should also make sure they don't leak data implicitly, so that our users can't infer associations from other teams by using these models. So search, what does that mean for search? So what we're trying to do in search is, given a query, we want to return the most relevant documents. Search in Slack is a bit different from something like web search. Again, the data set is not this big data set that's public to everyone. At the same time, it's also different from email search, where you're only searching over your own emails. So we're trying to make sure the user can find information within their organization, whether that's messages or files. The way we formalize that as a machine learning problem is as a learn-to-rank problem. So given a query from a user, we go to Solr, which is our document store, to retrieve a set of matching documents. And from there, we want to learn a model that outputs one score per document in such a way that if we were to rank the documents by these scores, we would end up with a list of documents that maximizes the user's utility given the query. In this case, the way we measure document utility is by looking at user interaction. So as if the user clicks or interacts with a document, it's seen as useful given the query. And the way we combine the utility of individual documents into a score for the entire list is using a bunch of different ranking metrics, whether that's mean average precision, NDCG, or precision at k. And what all of these metrics do is basically they give more weights to document that happen higher up in the list. So in the end of the day, what we're trying to do is make sure the document that the user is most likely to interact with appear at the top of the list. And the way we train this model is, since utility of documents is inferred from user activity, well, we join our click logs with the query logs, where we store all of the query and search results. From there, we have a labeled data set of, for every query, what are the documents the user interacted with, and then we can feed that into our model training pipeline and learn a model. But how do we do this in a privacy-preserving way, right? That's the real question. We have multiple teams providing logs, search logs, and we want to make sure the models we're using don't leak data between teams. And so you might say, well, that's easy. Just learn one model per team and you're done. The issue with that is that, well, first of all, this data is actually very high dimensional. If you look at a query or a message, there's a lot of different messages possible. And in Slack, there's a lot of, these messages have very different characteristics. We don't necessarily have that many query on a per team basis, especially for smaller teams. And so we're not going to have good coverage over all of our feature. And so that makes it hard to learn a meaningful model for on an individual team basis. There's also a lot of complexity in building individual models. We have over 500,000 teams. These teams range from a few users to Fortune 500 companies. That's a lot of models to train. That's a lot of models to tune. That's a lot of models to serve, to monitor. And so it's just not practical to do that on an individual basis. And so we know we want a global model, but we also want to make sure we preserve the privacy of our user. And so the technique we use is similar to a technique that was published by a couple of people at Google a few years ago called attribute parameterization. And the idea is to basically transform the features of our documents or the attributes of our document in a way that factors out the private information and reduces the sparsity of the data set. So here's an example. So we have a query coming from a user and then a document that's returned from Solar. And so the first step in most machine learning system is to extract features, right, or attributes. So for the query, we could extract, the user ID of the user who issued the query, the terms of the query. On the document side, we have the user ID of the user who posted a message, the channel ID of the channel in which it was posted, the terms in the message. And these are all one of the interesting characteristics of all of these attributes is that they're very high dimensional, right? So we have millions of users, so there's millions of possible user ID for the query user. Terms, again, queries can have different length. There's a bunch of different terms that are possible in queries. Same for the user ID in the document or the channel or the terms. And so one way to deal with this, one traditional way of doing this is like, well, let's compute a one-hot encoding of all these things, feed it to the model, and let the model figure it out, right? Let the model figure out how these different attributes interact with each other, let the model learn the representation for all of these attributes. And the problem with this approach for us is that if we do that and we let the model learn all of this, if we were to reuse the model between different teams, we would leak these association between teams, right? Going back to our layoffs example, if we learn from query terms and document terms, this association between layoffs and the company name, if we were to reuse that model between different teams, another team could infer that association through querying the model. So what we do instead is we take these high-level attributes, these high-dimensional attributes, and we compute function with the attributes that maps them back into a single-dimensional feature that generalizes across all the different teams and also factors out the private information. So for example, a simple one for terms would be the number of terms, right? Instead of feeding the terms into the model, we first compute a function, in this case, that would count the number of terms in the document and feed that into the model. So the model doesn't know what the initial terms were. The model only knows how many there were, which is not something we consider that's considered sensitive. And at the same time, by doing this, we know the number of terms would always be defined, right? It's defined for every possible example in our training set, and so we know we're going to learn something meaningful about this versus a very high-dimensional, vector of terms where each term might be set, only a few times in the training set. One of the most useful function for this is our CTR function. So for the CTR of an attribute of the document would be going back to our query log. When a document with that attribute was shown in search results, how often was it clicked, right? So clicks over impressions. One of the reasons this is very useful is it actually correlates really strongly with what we're trying to predict. So let's say we look at the channel of the document, for example. If we know how often messages from these channels are clicked when they show up in search result, that correlates pretty heavily with how likely we think the user is to click a message or a document from that channel in the search results. Again, this factors out the private information. The model doesn't know anything about the initial channel. All it knows about is the CTR. And the CTR is defined for every possible example. So again, we reduce the sparsity of our input data set, so it's easier to learn a meaningful model. This becomes more interesting when we look at CTR or functions of attributes across the query and the document. So in this case, for example, we could look at, well, when a particular user issues a query and sees results from a particular channel, how often does that user click on results from that channel? So what's the affinity between that user and this particular channel, and how does that factor into how likely the user is to click a document from that channel? Again, same thing here. We're factoring out the private information. We only feed the CTR into the model, so the model doesn't know anything about the initial user, the initial channel. And we can actually do this over a bunch of different attributes, right? We could look at the query user and the author of the message, or we could look at the query user and the people who reacted to the message, or at the team level, we could look at what terms get clicked a lot. And we still have to be careful. We can't do this blindly with any attribute. If we were to do this simply for the query terms and document terms, all of a sudden we'd be learning these association between words. And this time, instead of encoding them into the model, we're just feeding them straight into the model. So you have to use common sense and not, again, feed things that could leak data between teams. But one way you can get around this is just condition on one more attribute, right? So look at co-occurrences of terms, but give a query user so that this data is limited to just that user. And so the way we serve this at Inference Time is we can actually, for some of these functions, we can compute directly from the document or query. So for example, number of terms, we can compute directly from the document as it's being sent to the model. But for all of these features that are derived from more behavioral signals, we pre-compute those in on our data warehouse and then index them in our feature store so that they're available at Inference Time. And this gives us a lot of flexibility around what functions we want to compute over what attributes. It also allows us to compute those for different times. So we could look back, we could look at the logs for the past 6 months or the past 3 months or the past 7 days. We can use different decay functions. And really, we can compute all sorts of things and then index them and then just make them available at query time. And so that's it. So the way so how do we do this how do we train this ranking model in a privacy preserving way? Well, as mentioned, by learning from carefully crafted function of the high level or high dimensional attributes instead of learning directly from these attributes, we're able to factor out the private data before sending it to the model and reduce the sparsity to learn more meaningful models. So thank you. We're hiring. If you're interested, there's a link here, or you can come talk to me or anyone in the Slack booth later. Thanks.